Sometimes you write a piece of code, you execute it, and everything works exactly like you expected. Today's story is not one of the time. Last year I was writing a small demo for QuickBench. Here, quickbench.com. A few, not that much. I created were right, and so quickbench.com is a website where you can create your micro benchmarks and run them online. It's using Google Benchmark API, which looks like that if you never saw it. So you have this free function here, string copy, that takes a state as a parameter. You need a macro to declare it as a benchmark. And then you have this for loop. Everything before the for loop will be executed only once and is not benchmarked. That's where you put all the preparation for your benchmark. The for loop will be run multiple times. You have no idea how many. And it will be benchmarked. So here I'm building the first string hello. I don't benchmark it, and now I'm benchmarking how long it takes to copy it into a new string. That's how you create one benchmark. Sometimes you want something that's parameterized. For example, I want to see with different string sizes. Does everybody see the code? It's big enough? Okay. So here I'm running the same benchmark with strings of size 1, 8, and 1024. And most of the time when you run on a range, you don't really care which are the values between 1 and 1024 as long as you have a profile. So you can just use range, and Google Benchmark is going to choose the values in the range with something probably very smart. And in QuickBench, when you run this, you get this chart. So the x-axis is the range from 1 to 1024, and the y-axis is the time it takes. The higher we are, the slower it was. So yeah, as my string grows, the time it takes to copy it grows. So that's QuickBench. And last year I was writing a small demo. At the time, QuickBench only supported Clang 3.8 and GNU's implementation of the lib C++. And I wanted to show in 5 minutes how QuickBench can be useful. So I say, okay, I have this vector of 1 million random elements. I want to find the median using multiple STL algorithms. First algorithm that came to my mind, which is not the best, but the simplest, I just call std sort. I sort everything from smaller to bigger, and the median is just at the middle. When I want to benchmark that in QuickBench, I went with that. So we've seen this free function sorted, which takes a state. We've seen the for loop. Before the for loop, I'm generating a random vector. I do it before the for loop because that's very slow to generate random numbers. Inside the for loop, I'm sorting my random vector, except, as I told you, we have to run multiple times. If I were to sort directly input, I would sort it once, and then every other iteration would just run on an already sorted container. So I'm doing a copy before. That's great, but now I'm measuring two things. I'm measuring copy plus sort. So I did a second benchmark, which is exactly the same, except I do not sort. I just copy. I have this magical function called do not optimize in Google Benchmark, which makes sure that values is not removed by the compiler because nobody is using it. And when I run those two functions in QuickBench, I get this result. So in blue you have the copy alone, and in pink you have copy plus sort. And you probably cannot see the copy alone, which is very good news. It means our boilerplate is really not a problem. So I can get the median using std sort. I can also get the median using std stable sort, which, just like sort, sorts. The only difference is with sort, if I have two elements with the same value, I have no guarantee on the order, on the final order of these two elements relative to each other. With stable sort, if two elements have the same value, they will keep their relative order in the result. So in this example, I had bars with height and color. They are sorted by height. If I call sort on the color, I'm going to sort by color but lose the height ordering. With stable sort, I keep inside each color the height ordering of the color. That's an algorithm that will be used, for example, if you have UIs and you have Z orders and you want to order the window by Z order. If you have two windows with the same Z order, you might want to keep always the same order. So stable sort is a good algorithm for that. Stable sort is doing more work than sort. It's sorting plus keeping an order. So I expect it to be slower than sort. And when I run the benchmark, yes, stable sort is slightly slower than sort. Not that much. That's exactly what I expected. Now if I want to get the median, the real algorithm I should use is nth element. Sort and stable sort, I was just giving the container. Here I'm passing the container plus the position. At this position, nth element is going to put the elements that would be here if everything was sorted. Everything smaller is before, and everything bigger is partitioned after. So I don't know if it's very clear for everybody. If everything smaller is before and everything bigger is after, your element is sorted. It will not move if you finish sorting the full container. Is it clear for everybody? I know my accent is not perfect. Also, sometimes I might be a bit fast. Don't hesitate to ask questions during the presentation. On the other hand, if you know more than what I'm saying, wait until the end to say it, because you might be spoiling the end of the presentation. Nth element is sorting just one element. For the median, I'm just passing the center element. It's doing a lot less work, and it's 10 times faster. That's exactly what I expected. Great. Last algorithm I tried is partial sort. Partial sort is going to sort the beginning of your container. You give the container a position, and it's going to sort the smaller elements up to this position, and after that it puts all the bigger elements in no particular order. So it looks a bit like nth element, except everything on the left is sorted. And also the position you give is not sorted because it's like std sort. You're giving the end of the vector, not the last element. To find the median with partial sort, I'm sorting half the elements. So I expect it to be slower than nth element and faster than sort. I'm only sorting half the elements. And when we run in Quickbench, we get that, which is not at all what I expected. I didn't expect it because that's less work taking 50% more time than anything else. I didn't expect it for another reason. If you think about it, I just showed you nth element, and I just show you sort. If I call nth element with the central position, and then I call sort on everything before the central position, I'm doing exactly the same work as partial sort. That's the code of my benchmark. Just like sort, I'm getting the random vector, and inside the for loop, I copy, I take the middle in a variable, I call nth element plus sort. That's 3 times faster than partial sort. Which raises the question, did we in 10 minutes and 2 lines of code implement a better version of partial sort than the STL implementers did in 20 years? Yeah, the answer is probably no. And so let's find out why. When you find something you didn't expect, in an STL algorithm, the first thing you should do, first thing any programmer, no matter the level of expertise, should do is go check the contract. Go read the standards, which you can find on GitHub. You have all the draft of the standards. Or you can go on C++ reference, which I like because it contains the same information as the draft usually, but it adds comparison between STL and C++ version, I mean. It will tell you, oh, this algorithm was doing that in C++11 and that in C++17. When you're using the draft, you have to compare them manually if you want to see if something changed. And today we're going to look at the complexity part of those algorithms to begin with. I know almost all of you know what Bigelow notation is, but just in a few seconds, Bigelow notation is just saying what shape my performance have when I change the size of my data. Is it just completely independent, which is O of 1? Does it grow linearly, which is O of n? Or does it grow faster than linear? It could explode completely. That's what Bigelow notation is about. For example, the complexity of sort is O of n log n on average until C++11, and O of n log n guaranteed since C++11. So that's the kind of information C++ reference gives me, which is convenient. We'll use this result later. When you look at partial sort, you get that. Approximately last minus first, log middle minus first applications of CMP. That's a mouthful, and I don't find it very easy to read. So in Bigelow notation, that's O of n log k, with n the size of your fault container, and k the size of the subset we are sorting. And we just said, okay, Bigelow notation is how does my data grow when I add new data. But when my data grow with partial sort, it could happen two things. Either I'm always sorting the same subset, and my data grow, or my data grow and my subset sorted grows with it. Let me explain. In the case of the median, we have to sort half the elements. If I have twice as many elements, I have to sort twice as many elements. K is n divided by 2. And so my complexity is O of n log n divided by 2, which is O of n log n minus log 2, which is O of n log n minus n log 2. So we've said Bigelow notation is about the shape of my performances. When I add two different shapes, linear and O of n log n, the steeper shape is going to win no matter what. So here I can completely ignore the linear part, and it's just O of n log n. So partial sort has the same complexity as sort when I'm sorting the median. But that's one use case for partial sort. Another use case is I'm a video game programmer. I have a massively multiplayer online game. I have millions of players, and I want to show the 10 best players in the world in a scoreboard. In that case, k equals 10. So my complexity is O of n log 10. And log 10 being a constant, we don't care. It's just some linear data, O of n, which is a good complexity to have for an algorithm that sorts part of the data. Now, our implementation. It took us 2 lines, 10 minutes. We are calling nth element, which is O of n on average. And then on the result, we are calling sort on the k first elements. So our implementation is O of n plus k log k, which in the median scenario is O of n plus n divided by 2 log n divided by 2, which is O of n plus n log n, which is O of n log n. That's the same complexity as partial sort. And in the case of the scoreboard, we have O of n plus 10 log 10. 10 log 10 is a constant, we can remove it. We have O of n. So, conclusion, no matter how good you are, you should always check the contract. We just did it, and we didn't find anything. But we did the good thing. That's Great. So we have to go deeper to understand what's happening. And to go deeper, something programmers love when they don't understand the results, we really love it, is saying, oh, that's a compiler issue, or that's an STL implementation issue. There is a bug in my STL. Sometimes it's true. Sometimes. So let's check if it's a compiler or an STL implementation bug. For that, most programmers go on Compiler Explorer. We .bolt our code. Or you can go on OneBox if you need to execute the code. Here we were in QuickBench, and luckily QuickBench allows you to change the compiler and the STL implementation. So we are just going to stay in QuickBench. We're going to try with GCC instead of Clang. GCC 5 gives exactly the same kind of result, multiple times faster to use our version. A more recent GCC version gets exactly the same result. Now if I change the STL implementation, I go on LLVM implementation of the libc++, same result. And if I go on a recent LLVM implementation of the STL, same result. And if I leave QuickBench and I go on Windows and run it in Visual Studio, I'm also faster than the STL implementation. So sadly, it's not a bug in my compiler. I have to go deeper. So we found this difference. We found this very good result for our implementation for 1 million elements and sorting half the elements. That's exactly one scenario. And partial sort, its job is to cover a lot of scenarios. So let's measure what happens if we have other scenarios. And in your day-to-day job, if you need to compare, you can use Google Benchmark, which is very powerful on GitHub, or you could use QuickBench. It's my tool, so I encourage you to use it. And yeah, so we had this scenario, 1 million elements. I'm sorting half the elements, but we could sort a different number of elements. We could have a different size of container, and we could have both changing at the same time. What happens if I keep 1 million elements, I sort a different number of elements? So 1 million elements, I vary a subset, I get that. So x-axis is the number of elements I'm sorting inside 1 million. On the left-hand side, I'm sorting nothing. On the right-hand side, I'm sorting the full container. The orange line is sort. STD sort is always sorting everything, so it's an horizontal line. In blue, you have our implementation. When we sort nothing, it's pretty fast. When we sort everything, it takes the same time as STD sort, because that's exactly what we're doing. Partial sort is in pink, and it doesn't look good, right? I mean, when I sort 1/4 of the element, I'm already slower than sorting everything with STD sort. That's not very good, but if you look very closely on the left-hand side, you might note that the blue and pink line cross. And if I zoom in, I show only what happens if I sort between 0 and 10,000 elements inside my 1 million container. Here, partial sort is at least 10 times faster than our implementation. We finally have some scenario where we completely see the point of the STL implementation of partial sort. Another scenario. I am sorting a fixed number of elements, and I have a container that grows. That's what happens with my MMO earlier. I'm always showing the 10 best player, but I have more and more players joining my game. So in this benchmark, we are going to sort just 100 elements inside the container. And bigger notation, you can clearly see it here. The orange line, STD sort, grows in O of n log n. On the other hand, both nth element plus sort and partial sort are growing linearly O of n. And they might have the same complexity, but clearly partial sort is way, way faster than our implementation in this chart. Once again, the STL implementation makes complete sense in this scenario. Last scenario, I have a container that grows, and the subset I'm sorting grows with it, which was the median case. Let's make a benchmark where I just sort 1/5 of the element, and I grow my container. So in orange, still sort. It's always woven log n, it didn't change. And in pink, partial sort is taking almost the same time as sort, while it's only sorting 1/5 of the element and not everything. Nth element plus sort, on the other hand, is doing pretty well. So if we finally found scenarios where STL implementation made sense and STL implementation doesn't make sense in other scenarios. If you were to leave the room right now and go back to your work, you can already take something with you, which is, when should I call partial sort? You should call it when you are sorting a small number of elements in your full container. On the other hand, if you are sorting a big chunk of your data, call nth element and then sort the result. I hope you're not going to leave the room immediately. And if you're like me, you want to understand how and why we have this result. To find that, I need to make sure we all have the same items with us on this journey. I'm going to show you 3 famous sorting algorithms that you probably know, but let's make sure everybody knows them. It will not be very long. First is insertion sort. Insertion sort, I have a sorted container in blue. I add a new element at the end, which is in dark blue and white border. I'm going to shift this new element towards the beginning until my full container is sorted. Great. What happens if I have a huge container that isn't sorted? I'm just going to say, hey, the first element is a sorted container of one element. Makes sense? I'm adding a second element. I'm going to shift it and add a new element and shift it, and so on and so forth. And after a long time, I'm going to have sorted everything. I have n element to sort, and each element might have to shift up to from the right to the left. So it's O of n square in complexity, which is not very good for a sorting algorithm. On the other hand, I'm just swapping elements, so it has no memory consumption, and negligible memory consumption. Also, I'm reading everything contiguously, so it's very good for CPU cache. Who in this room thinks std sort is calling insertion sort? Nobody. Nobody. Oh, one hand. Quick sort. This one, you probably heard about it. You have this full container that's randomized. You choose one element. It's a pivot. You are going to partition everything around the pivot. Everything smaller is before, everything bigger is after. That's pretty fast. And you're here. And once you're here, the pivot will never move again during the sort, because everything after is bigger, it will never go to the right. Everything before is smaller, it will never go to the left. So I just fix it, and I'm going to choose 2 new pivots on both ends of the fixed element. I'm going to shift around them, and so on and so forth. And very quickly, I have sorted everything. On average, I'm going to recurse log n time. And each time I'm going to partition everything, so it's O of n, so the result is O of n log n. It's very quick, because partitioning everything is very CPU cache friendly. You're reading contiguously in memory. And also, quicksort does very few swaps in most scenarios. Also, I'm always doing swaps, so I don't have memory consumption. I don't have to copy the correction at all. Thing is, I told you we are going to choose a pivot. Choosing a pivot is a full presentation by itself, which I'm not going to do now. Just what happens if, for my first pivot, I had chosen this element. It would end up here after partitioning. If I choose the second element, it ends up here. And third element, which is the smallest, it ends up here. And each time I'm recursing only on one side, because there is only one side to my pivot. If it happens all the time, I will be O(n) square. Clearly, there are good strategies to choose a pivot where it will almost never happen. Sadly, when your programming language is used to develop operating systems and servers, people are going to build containers that are made to be slow with your pivot strategy. So that's clearly a real danger. Knowing that, who expects stdsort to be calling quicksort? A few hands, not that much, but yeah, we have hands this time. Last sorting algorithm, heap sort. So a heap is a balanced binary tree, which means it's a tree with every node has at most 2 children, and balance means that we cannot create a new level if a level is not finished. So here, 5 is the only node that can have children, where I can add new children for the moment. And the heap is a balanced binary tree that has just one condition. The children of a node are always smaller than the node itself, than its parent. So that means my maximum is always at the top, because it cannot be the children of any other node. And with just this condition, we can do interesting things. We can very easily insert a new element. We just put it as the first available position. We are breaking the contract here, so we are going to swap. And we swap for the new contract break. In 2 swaps, we have remade a correct heap. It's always log n worst case scenario to add an element, which is pretty fast. And the other operation I can do quickly is pop. I can remove the maximum. When I do that, I'm missing an element, so I'm going to take the last child, put it instead, and swap with the biggest child if I have to. And once again, the worst case scenario would be to have to swap twice in this. So it's always log n. And another interesting fact is that balanced binary trees can be put inside a flat container. You just find the children by taking the index of your node, multiplying by 2, and multiplying by 2 plus 1. Heap sort, I'm just going to take all the elements, put them in a heap, and then pop them one by one. So I have this unsorted container with values. I put everything in a heap. I swap when I have to. And then I'm going to pop the max, rebalance, pop the max. And that way, I will get my sorted container. The great thing is it will always be O(n) log n. The bad thing is it's 4 or 5 times slower than quicksort in most scenarios. Why? Because first, we are swapping a lot more than quicksort in most scenarios. And also, as I told you, when you have a node, you can find the child by multiplying the index by 2 and multiply by 2 plus 1, which means that each time you do that, you are going to make a cache miss. So it's very bad for your CPU cache. On the other hand, as I told you, a balanced binary tree can be put inside a vector. So in fact, we are working in place, so we don't copy anything. Knowing that, who expects stdsort to be calling heap sort? And I have about 10 hands. So, the answer. You can read the code of the STL algorithms by going to GitHub and reading GCC's implementation. You can also go to GitHub and read LFVM's implementation, or you can just go in Visual Studio, you go on the name of an algorithm, you press F12, you're in the header, and you read the code. Today we're going to read GCC's implementation just because it fits very well in my slides. Actually, they all use the same algorithms to do that. So std sort, how is it implemented? That's GCC's implementation of std sort. It's pulling into a sort loop. I just show you 3 sorting algorithms, and now I'm telling, oh, it's into sort, which I didn't present. Did I just waste your time? Earlier, we've looked at std sort contract, and we've said it was O of n log n on average until C++11, and now it's O of n log n guaranteed. The problem is quicksort is O of n log n on average. It doesn't respect the new contract of std sort. Heap sort is 4 or 5 times slower, but it respects the contract. So intro sort is just going to do both. Yeah. So intro sort is going to call quicksort, and we are supposed to recurse log n time. We are going to recurse 2 log n time. After 2 log n time, if we still don't have our sorting container, we say, okay, we have a problem with this pivot strategy, or somebody is attacking us, I don't know. And then you fall back on heap sort. That means that no matter what happens, you are going to be O of n log n. And on top of that, most of the time, you are going to just do a quicksort, which is very fast. That's super smart, if you ask me. It gets better. std sort, it is. Why? Why call an O of n square algorithm at the end of sort? The idea is, I told you, yeah, quicksort is very fast because you are partitioning everything contiguously. That's true for the first recursion. After some time, you are recursing in very small buckets, which are at different places. You have places where you have already sorted everything, so you have this small bucket of 8 elements, and then further 5 elements. At this point, it's not CPU cache friendly at all. So what they say is, they say, okay, we are almost done sorting with quicksort. Every bucket is maximum 16 elements large. At this time, if you call insertion sort on everything, the worst case scenario is my element is going to move 16 away from its current position. So the complexity is not O of n squared, it's O of 16 times n, which is O of n. And also it's super CPU cache friendly because this time we are doing everything contiguously in memory. So insertion sort is faster than quicksort in very small buckets. That's, if you ask me, that's very, very brilliant fine-tuning. Nth element. How is nth element implemented? We are calling intro select, which you don't know. Well, intro select is calling quick select, then falling back on heap select. You don't know those, but I think you see where this is going. Quick select is a simplified quicksort. In quicksort, we were choosing a pivot, we were partitioning around it, and recursing on both ends. With nth element, when you have partitioned around your pivot, first question is, did my pivot end up at the nth position? If it did, you're done. Your element is sorted, everything smaller is before, everything bigger is after, you are finished. If it isn't, you just need to recurse on the side of the pivot where the nth position is. The other one is sorted enough for what you want. So here I'm looking for this pin position. I choose a pivot. I'm not super lucky, so my pivot is not going to end up directly in the final position. But I just have to recurse on the right-hand side. And with 3 recursions, I found my nth element. So that's very fast. That's very fast when I choose my pivot correctly. If I once again have a problem with my pivot strategy, I could be O of n squared, which for a selection is really bad. So I can fall back on heap select. On heap sort, we were putting everything in a heap and then popping. This time we just build a heap of n elements, n being the position I'm looking for, with the n first elements. And then I'm going to compare every element that isn't in the heap with the maximum of the heap. If they are smaller than the maximum of the heap, I'm going to pop the maximum, put the new element in the heap. When I've compared everything, the maximum of my heap is the nth element, because everything inside the heap is smaller, and everything outside of the heap is bigger. So that's the nth element. I don't have to pop everything, I just pop this one, and the tree is good enough. Also, yeah, it has negligible memory consumption once again. Final algorithm we want to read, partial sort. The explanation of what we've been looking for. Partial sort is calling heap select and heap sort, which should surprise you. I mean, we are calling a sort algorithm which is slower than quicksort, and then a selection algorithm which has a worse complexity than quickselect on average. Why are we going with a slow sort algorithm and a complex select algorithm? And to explain that, I'm going to show you my last benchmark today. 1 million elements, once again, and I change the position I'm looking for. I'm zoomed in here. I'm going only from 0 to 40,000. I could go up to 1 million, and the blue line would continue to grow farther and farther from the pink line. The pink line is quick select. It always takes the same time because it's O of n. It doesn't care about which J position I'm looking for. Heap select is more complex. Clearly it grows with J and it will explode. But complexity is not everything. Here from 0 to 15,000, clearly heap select is faster than quick select. And that's what the STL implementers were looking for. They chose an algorithm which has very good performance on low K values, even if they knew that it had a bigger complexity on high K values. I think it's interesting at this point to take a step back and think about what we've been trying to understand. What is nth element? It's an algorithm you use to find a median. That's the algorithm you use if you want to find the first decile of a distribution, or if you want to find the last decile of the distribution. Nth element, you have to have an algorithm that's independent of K, because you might have huge values for K. On the other hand, partial sort, we've been using it to find a median. That was for a demo. It doesn't make sense to search for a median using partial sort that nth element work. Partial sort, actually you use it because you have a search engine and you want to sort the 10 best results by page rank. You use it for the 100 best player in your MMO. You use it to, I don't know, sort the 15 richest people in the world because you're doing a magazine on the richest people in the world. All the time, you have very small K values and huge data set. So it makes complete sense to choose an algorithm that will perform well in these use cases. I find it interesting because when I started researching for that, in my mind, STL implementers were thinking completely generically. They were searching for the best solution. The best solution doesn't exist. Actually, they are fine-tuning for real use cases of their algorithms, not some kind of best case for everything. And when they chose an algorithm which was slow for pet examples, but very fast for actual use cases, they knew exactly what they were doing. I hope that with this presentation you do too. Thank you. And we have some time for questions. And we have a second mic.
Another mic over there. So you showed the implementation of the partial sort, which was first find heap select and then heap sort. Why not replace the heap sort there with std sort, which should in theory be more efficient?
the reason I think, I didn't do the benchmark myself, but I think the thing is you already have a heap. So the heap sort you're doing is just the popping part of heap sort. You're not doing the full heap sort. You already built the tree to find the select. So now it's probably faster to pop everything than call quicksort.
Thank you.
So you did your benchmarking with vectors of integers, right?
Yes.
So my question is, how did you look at the influence of the element type? So we did some assumptions on cache friendliness.
Yeah.
Size. In fact, it's
yes.
on the copy constructor of those.
That's a very good question, by which I mean that no, I didn't. No, yeah. In fact, that would be very interesting to compare and see if the difference is that huge if elements are very big and not just int in memory. No other question? Okay, I can add a little thing. I don't have a slide for that, but I said it doesn't make sense to search for a median using partial sort. In fact, I found that Google Benchmark was using partial sort to find the median because there is a partial sort copy and there is not an nth element copy or a sort copy, and so they were doing that. In fact, it's way slower than just copying absolutely everything and then calling nth element on the result. And yes, objects were a bit bigger in that case, but it doesn't change the result. Yes.
Any ideas why standardization committee decided to change the complexity in standard for
STD sort?
STD sort.
Yeah, because I think at the moment where they changed it, everybody was doing intro sort, and it's better to have something guaranteed that than something that might completely explode if somebody is attaching you. So I say, okay, all the big compiler implementers, the big STL implementers already do it. Let's go with that. I think there is no downside, I think, to removing this on average once. Oh, there is?
Then why they didn't provide, I don't know, separate implementation of just quick sort without such guarantees, because usually quick sort is faster than additional, with just as the sort with additional checks for recursion depth and so on.
Yeah, but if you're calling into sort and you don't have a problem, you are doing quick sort. I mean, you fall back on heap sort only if everything is already crumbling around you and there is already a big problem. Because we are recursing 2 log n times, which should find the solution, especially knowing that we don't recurse into small buckets. So in fact, you win a few recursions by not sorting. So you're always doing the quick sort, except in some very, very rare cases.
Yes, but you have to calculate logarithms and so on, because I think that if you want to sort like 100 elements of integers, something, it's considerable.
You think the 2 log n calculation makes a difference? You can, actually, there is nothing stopping you from directly calling the STL. I mean, yeah, there is something stopping you, which is that you want to do perhaps your code to work on different compilers, but you can try to call the intro sort loop with a huge value instead of std log multiplied by 2. And
yes, but
this
it's a private
it's a hack.
function with double underscores. in front of, and
Yeah.
study says that you cannot
it's
use
hard.
it. And
But we could try benchmarking it, yeah. That would be interesting to see at which point calculating the log is really a problem. Thank you.
Thank you.
Do you have the code for this benchmark still available so we could test it with, e.g., Boost spread sort or something like that? Because I think they say it only makes sense after 1,000,000 or 1,000 elements.
Yes, okay, so you can get my slides on Meeting C++ website. I already gave the link. And inside the presentation, next to each, it's HTML, and I have commented next to it the path to each benchmark. So if you get the slides, you can find the benchmarks, yes. No other questions? Thank you.